All right. So now we're actually going to start talking some physics. We're going to start by modeling the most basic kind of motion we can, which is when an object moves in the same direction at the same rate. So to begin, we're going to define the average speed of an object as the rate that the object is covering distance. So if you time for a certain interval, this would be sort of starting and stopping a stopwatch, measure how far the object has gone. You can divide those two and get a distance per time, which we call the average speed. So this would have units like meters per second, centimeters per second, miles per hour, etc. And basically everything in this class we'll just call an object to avoid dealing with complicated pictures and the motion of individual parts. Everything is basically an object, meaning just pretend it's a dot. There will come a point where we do care about those things when talking about rotation, but basically everything is just box my eyes. Now we can also define, similar to speed, we can define the velocity of an object as not just the speed, but also a vector with orientation. So not how fast are you, but how fast are you and in what direction. And the average velocity is defined in a very similar way. We just don't use the scalar displacement, but instead the vector, or sorry, not instead the scalar distance, but instead the vector displacement. Now, these give what are called averages. Now, it's different than the average in the sense of like a sum. Now, there really is like connection there if we know some calculus, but we want to think of the average sort of a general estimate of what's going on, like how your grade is an average. It tells you overall how you're doing, but it probably doesn't tell you anything about specific assignments. So, what we can do is if we don't want the average, but instead want what's called the instantaneous speed or instantaneous velocity, we just zoom in, zoom in, zoom in with these delta t's so that we're timing really close together. Think of it like the FPS on a camera, right? If you're recording at 10 frames per second, you're getting a really choppy movie. And there's a lot of skipping, and you're missing the in betweens. If you record at 60 FPS, it's going to be a lot smoother. So as you decrease this delta t, you get a better and better estimate of what's going on at any specific time. And that's actually a fundamental calculus idea. So let's start. A runner completes one lap of a circular track of radius 31.8 meters in 100 seconds. The runner moves at constant speed. Calculate the distance traveled by the person. Okay, what is the distance? So we're basically asking how far did the runner move if they complete one lap of this circular track? Well, we have a name for that. That is the circumference, which if you check your formula sheet, that is 2 pi r. Now, here and here only, we'll do a 3.14 substitution for pi. Just because it's all numeric, I'll just write it out. All right, why did I pick this number? So you'll see that I try to make all the numbers work out nice. And sometimes even I forget why I did that. So let's see, is this going to be nonsense or does this work out to something nice? Oh, this is basically 200 meters. Thank you, me from the past. So let's calculate each of the following. What is the average speed of the runner versus average velocity? Average speed, there is nothing weird that ever happens with average speed. It's just d over t. They traveled 200 meters and it took them 100 seconds. So they go 2 meters every second. Pretty straightforward. But what is their average velocity? Hmm. Well, let's look at the definition. Average velocity is a vector, and it's their displacement divided by time. Okay? What is the runner's displacement over one full lap? Well, they started here, then they move all the way around and ended. So they actually displace no net distance, meaning, yeah, it took 100 seconds, but they went nowhere. They went 0 meters displacement wise in 100 seconds. So their average velocity is actually 0. You know what? I like writing it out. So if you don't displace any distance, it means your average velocity is 0. And we'll talk about that more with this next part because it says, is the instantaneous velocity ever 0, even though the average is? So instantaneous velocity is speed plus direction. That would mean, well, here they're moving 2 meters per second. Here they're moving 2 meters per second. Here they're moving 2 meters per second. And so on. And here they're moving 2 meters per second. So notice that, why is the average velocity 0? Well, notice, because it's a vector quantity, you're asking what way on average are they moving? Well, they can't be moving up on average because it gets canceled by the down part. They can't be moving right on average because it gets canceled by the left part. So yes, even though they're always moving, their average is 0 for this velocity because every velocity vector has a friend on the opposite side of the clock that cancels it. So is their instantaneous velocity ever 0? No. They're always moving. So they are always moving, but their average velocity is 0 because the directions are canceling to make it 0. There's a common physics joke that if you die in the hospital you're born in, your average velocity through your entire life is 0. I'm sure that's lovely to think. So now when modeling motion, we have several ways to do it. We could write about it, straightforward. We could make a dot diagram, which, going back to my camera idea, this is like taking snapshots at a certain FPS. We have motion graphs where we plot something about the motion as functions of time, or we explicitly just write a formula as a function of time. So all of those things for a constant velocity scenario are as follows. If your FPS video, when you go click, 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 your distances are increased or are the same amount every second. So notice that these spacings are the same. This is what's implying constant velocity. We will talk about in the next problem. If you make a linear position time graph, right, because you're going up by the same amount every second, this is because your velocity is the rate of displacement. So if you have a constant rate of displacement, constant rate is always a straight line idea. So that's why we get a linear graph. And as a result, any functions must follow a straight line form. Because if you're going to start at some value and then go up or down by the same amount every second. So it must follow y equals mx plus. So we're going to do this here. A toy car traveling to the right generates the following dot diagram. Adjacent tick marks are separated by 1 centimeter and spaced by 0.1 seconds in time. So this is the key with a dot diagram, is they're spaced equally in time, like the frames per second on a camera. So it's convention that we start at 0, and every click, I say click because I think of these in my lab as spark timers. We have equipment that does this where you attach this special tape, pars or things in the lab, and they'll drag them through the timer and it goes click, click, click at a constant rate. So we made the claim on the other page that since the dots are uniformly spaced, this means constant velocity. Why is that true? So it definitely has the fact to do with the distances being the same, right? Because we know that velocity in the case of 1D would be delta x over delta t. So notice that since the gaps are the same, it means we have the same delta x every time interval. And since the dots are evenly spaced, we can also conclude that it's the same delta t. So since the dots are uniformly spaced, we travel the same distance between each interval. And also, since the dots are equally spaced in time, we go same distance, same time. So therefore, same d, same t. So d over t is the same. So now let's fill in a little table for us here. Do some ruler reading. Oh boy, how engaging. We're about to see if I can make diagrams properly here. So we start at 0, right? We see that's nice and aligned here. So we see this is at 1, 2 tick marks, 3, 4th tick mark, 6th tick mark, 8, and 10. Okay, lovely. It does count up by the same amount. 2, 4, 6, 8, 10. So notice we can already see this sort of slope idea happening as to why we know that this is a constant speed motion, because every time, right, +2, +2, +2, +2, +2. But I can't just stop there. I have to make sure I'm spacing these out uniformly, which I am, right? Plus 0.1, plus 0.1, plus 0.1, and so on. Now, notice these look like, from algebra, sort of these rise over run tables. And notice that anytime I divide the differences, they will be the same number. So let's sketch it. Pretty straightforward. I started at 0, and then every click I went up by 2. Yes. Do not connect things with lines unless if you're explicitly told to do so. We're just going to plot these at data points here. Although we do have reason to believe that this is a linear relationship, so I have no qualms actually just drawing in the line here, because that is the point of the problem. What is the average speed of the car? There's a million ways of doing this. I actually just like it using the graph. So S is just going to be d over t, which is going to be the slope, which is going to be rise over run, which is, my graph went up 10 centimeters in over 0.5 seconds. So 20 centimeters per second is my average speed. So now we can do this to write a function for where the car is as a function of time. So since we know that this is linear, we know that I can write this in y equals mx plus b form, right? Because the slope, this is the rate, and then b is your starting value. So in this case, we're modeling x of t, not y. So the position, x of t, is equal to, what's the rate? Well, the rate is the slope of our line, which we just said was 20 centimeters per second. And where did we start? 0. So we can write the relationship that the position x is just 20 times t. So notice this works no matter what t you plug in, right? If I plug in 0, I get 0. If I plug in 0.5, I do get 1. If I plug in 0.2, I get 4. You can check all this. So this is kind of a trippy thing to talk about. Sometimes we're actually going to look at motion from different perspectives, which is kind of known as a reference frame. It's sort of where you're observing the motion from. Standard choice in 99% of problems is called the lab frame, where you're just think of someone just watching an experiment take place. But sometimes it's useful for one reason or another to sort of enter another object's perspective, where all velocities will appear to shift relative to you. What I mean by that is, if you're driving in a car, it's pretty easy to convince yourself, looking out the window, you can just pretend that me in the car, I'm actually not moving. It's everybody else. moving relative to me, right? If you look out your window, you'll see trees moving backwards relative to you. Now, someone in the lab frame would say, no way those trees are moving, but you in the car think they are. So different observers are going to disagree on what the velocity of things are, and that's fine. We're just going to talk about how to convert. I do not like using formulas for this. I will just sort of show you how this works in context. Basically, how I like to think of velocity transformations um, is if you're entering the frame of reference of an observer that's moving, every other object gets a boost in the opposite direction equal to your velocity. What do I mean by that? Well, you can think of converting by basically adding the reverse of your velocity to everything. So in the lab frame, somebody sees car A moving 2 meters per second left, car B, right? Sorry, cannot read. Car B moving 8 meters per second left. Now, if I go to frame A, we can think of giving everybody a boost opposite of car A's velocity. So I'd boost car A 2 meters per second left. I would boost car B 2 meters per second left to enter car A's frame. So notice that as a result, I get 2 left, 2 right. Velocities cancel because they're vectors. Left and right cancel. And then 8 and 2 add to make 10. And that makes sense because if you're entering car A's frame of reference, it should see car B traveling at it faster because this is going to be a head-on collision. Just to illustrate this, we have a pretty typical example where we're just going to compare speeds in different reference frames. So we have 3 toy cars moving on a straight line. This is the lab frame, and we're going to enter the car frames and see what all the measured speeds are. So in car A's frame, car A is moving 1 meter per second right. So I got to boost everybody by sort of -1. So notice, as expected, of course, the boost cancels, so RA doesn't think they're moving in their frame. Then 2 right, 1 left, adding them vectorially, we get 1 right. And then car C, 3 left, 1 left, 4 left. So notice that car A sees car B moving away from them, which makes sense because car B is moving faster than car A in the same direction. So car A sees car B moving away and car C moving towards it. So that works. Now, car B, well, for car B's reference frame, it's also moving to the left, but at 2 meters per second. So we can just change this. So, of course, as expected, the 2's go away. Car B doesn't think they're moving. And if they observe, they actually see car A moving backwards at 1 meter per second because -2 and 1 is -1. And they see car C approaching at, what is that going to be, 6? 5. So again, 1 right, 2 left makes 1 left. 3 right, 3 left, 2 left makes 5 left. So car B actually sees car A moving backwards relative to them because they've sort of passed car A. And then lastly, we have car C, which is moving at 3 meters per second left. So everybody gets a boost 3 meters per second to the right applied. So car A, that's 3 plus 1 is 4. Car B is 3 plus 2, which is 5. And car C doesn't think they're moving. So this is just some practice with converting to reference frames. Sometimes it's helpful, as you'll see, but This is just the idea that we can look at the motion from any observer's perspective that we'd like. All right, this is a classic one. It's already been pointed out to me that 6 meters per second is a ridiculous speed for a river. Try to do things that are physically reasonable, but sometimes we make mistakes. A river flows at a velocity of 6 meters per second west relative to the shore. We have a boat that is at A and wishes to go to B. The boat can output a velocity of 10 meters per second relative to the water, meaning I have like an arrow of length 10 that I can direct however I want along this path. And of course, the river is going to influence sort of which way I go. So, draw the path if the boat directs its velocity due north. Because that might be your first thought. Like, I'm trying to cross the river. I want to get from A to B. So, why not just put my velocity straight north? Right? All 10 meters per second of my velocity due north. Well, that forgot to account for the fact that the river also has a velocity. And these will add as vectors. So my velocity won't be 10 meters per second due north because I forgot about the river. So the river also sends me a bit west. So this would not get me to point B because this would send my velocity at some sort of an angle. So I wouldn't be moving in a straight line because I'm not changing my speed or direction, but it's not where I want to go. So what do I have to do instead if I'm trying to get to point B? Well, it should be clear from this picture that if you went due north, you sort of miss it this way. So what the boat has to do is the boat has to cancel the river velocity. So the boat wants to put its velocity this way in order to cancel the component from the river. So I said boat must have a northward component, obviously, right? If the boat wants to go north, you must be going north. But also, it has to have an east component to cancel the west flow of the river. So that's why you actually need an angled vector there. Anytime you just have quadrants, you just got to get the right sort of the right of the four. We can also split into octants sometimes, and we could grade you on that, but usually you just got to get up and right. So let's calculate everything. What is the east-west component of the boat's velocity relative to the water? What's the north-south components? Net velocity, time, all of those fun. All right, so what did we determine? Well, we just determined that to cross the river, the boat definitely needs to cancel the river's velocity. So we know that the boat can only output 10 meters per second. And we also know that the boat must go 6 meters per second east to cancel the river. So we know that this must be the eastward component. And what's the north-south component? Well, we now have two of the three sides of a right triangle. So we can use the Pythagorean theorem to get the third side. And here's our daily drop of the 3, 4, 5. I mean, it's a 3, 4, 5 cousin, but so we know that 6 squared plus, we'll call this Vy squared is equal to 10 squared. Notice this is a 3, 4, 5 cousin because Vy would be the square root of 100 minus 36, which would be square root of 64, which would be 8. And I say that it's a 3, 4, 5 cousin because 6 is 3 times 2, and 8 is 4 times 2, and 10 is 5 times 2. So this is a scaled multiple. So that's why we have like a crazy river speed, because I was very set on making this a 3, 4. All right, what's the net velocity of the boat relative to the shore? So this just means let's add everything up. So our boat velocity looks like this, where we said there was 6 meters per second this way, 6 meters per 8, 6 meters per second this way, 8 meters per second this way. So this is the boat relative to the water. And then we also had the water. This. So if we add these together, notice that the 6's cancel, so we get 8 meters per second due north, which is exactly what we wanted, right? We wanted the boat to go undeflected north. So that's just sort of illustrating why we did the process we did. And then how long is required for the boat to cross the stream? Well, if we look here, we see that the boat is going 8 meters per second north, and it must cross a distance of 800 meters. So since this is constant, we know that Vy is just d over t. So Vy times t is equal to d, or t is equal to d over v, which I'm sure you could have done in your head, but this would be 800 meters divided by 8 meters per second. Wow, look at that. It's a nice number. Me, did it right. 100 seconds. So that's a pretty common problem to know how to do, is these sort of relative velocity vector addition type. Now, this is a favorite of mine. This is our first introduction to one of the free response types. You'll see almost all of my problems are kind of written in this form when applicable. It's called a qualitative quantitative translation, or a QQT, where we have to predict something without doing math. We have to do some math, make sure everything agrees, and then reflect. Good physics almost always involves aspects of it. So we got two runners, A and B, where they're starting at opposite ends of a 300-meter long road. A has a speed of 2 meters per second, B has a speed of 4 meters per second. They're coming at each other, and they're going to pass each other. And we have to pick, where are they going to pass? Are they going to pass on A's side, or are they going to pass on B's side? Because 150 is the midpoint. Now, if their speeds were equal, the answer would be the midpoint, right? Because you're going the same speed. So, of course, you meet right in the middle. But the speeds aren't the same. So, there's a variety of ways that you can do this. I asked this question for years. So, I've had a lot of student responses to this. I think my favorite response is that since B's moving faster, they're just going to reach the middle first, right? So since B is faster, they're going to be in the middle, and A is going to be not at the middle. So they're, of course, going to meet on A's side of the track. So that is my favorite response to that, I think. Runner B is faster. They cover more distance in the same time, so they reach the midpoint first. So they're on A's side. Let's sketch a graph of the position of each runner as a function of time. Let's label each curve. So there's no grid lines here, meaning we just want like a rough shape. You don't have to get anything right. If there are grid lines, we do expect accuracy. So A starts at 0 and moves towards the 300 end. So this would be A. And then B, they don't start at 0, they start at 300. So they actually get a y-intercept. And technically they should be like moving faster, so they have like a steeper slope, but that's not something we could accurately reflect on this diagram, and this would be B. So we can see we're really interested at the time and position of this like crossing point here. So this should be bringing up some thoughts of like linear systems from algebra. So what is each position as a function of time? Well, these are linear, so it's going to be y equals mx plus b. So for A, notice that runner A starts at 0, and it says that they gain 2 meters every second, so plus 2t. Runner B starts at 300, and they're gaining 4 meters every second, But we have to be careful because their x value is not going up, their x value is going down. So we actually write this as negative t. Because again, negative in physics, if it is a vector, just tells you which way you're going. It doesn't mean they're going negative speed, right? Velocity is a vector, so that's how we reflect that. All right, when do the runners pass each other? Well, if they pass each other, their positions are the same. So that means we can just set these quantities equal. So 2t equals 300 minus 4t. So 300 is equal to 6t. Divide. Another nice number. Thank you, me. So it is possible to do this sort of linear systems approach, but since we've been talking about reference frames, I actually put this problem down here because we can actually solve this by entering the reference frame of one of the runners. What I mean by that is if I am in A's frame of reference, I think that I'm not moving. If I'm runner A and I'm in my frame of reference, I think I'm not moving. But what I do observe is runner B, which I give the reverse boost, right? So when I reverse boost myself, I don't think I'm moving. And then when I give runner B the reverse boost of 2 meters per second, it looks like they're approaching me at 6 meters per second. So if I do that, I actually observe runner B moving at me at 6 meters per second. And now it's not even a 2 variable problem, it's just one, right? Because I think I'm stationary. I see somebody coming at me at 6 meters per second for 300 meters. So I just know that E equals speed times time. So 300 is equal to 6 times t, and we do get the same result. Now notice that that is encoded in the fact with these opposite directions that when I had to combine the t's, the velocity terms added. So that works out. All right, where do they pass each other? Well, this just involves plugging in. Oh, let's see. So you can pick either function. So we said that x of a was just 2t plus 0. So if I plug in 50 to that function, I get 100 meters, which is noticeably not the midpoint, right? It's closer to A. And we better get the same result for B, or we totally messed up. So let's check that, if I can write properly. Yep, we do get the same result because negative 4 times 50 is negative 200. Cool. So we checked using both runners that it does work. Now we can also find x pass using a really clever approach where we don't do any functions, we just sort of think about it. And whenever I find a cool think about it problem, I'm just going to show it to you because I think it's good for building our physics skills. So what I mean by a ratio approach is sort of thinking about what happens when they pass each other. So we already know that they're going to pass on A's side. So they're going to pass maybe like here. We can call this distance x pass. So what we mean by a ratio approach is we just think about the fact that since runner A is moving at half the speed of runner B, well, that means that if runner A went this distance, x pass, runner B must have went twice that distance. And also, using our good old friend segment addition from geometry, we know that the whole distance was 300 meters. So we know that x pass plus 2x pass is equal to 300 meters, or 3x pass is equal to 300, or x pass equals 100 meters as expected. This is a cool ratio approach. A quadratic version of this shows up with gravity. And this problem shows up sort of again, kind of with electric. But this is a cool idea, so I thought I'd show it. All right. This is the first time this has happened so far. This is technically in scope for Physics 1, but this is more of a hard problem slash mechanics. So you can feel free to call it for AP1 here. But if you want to do a difficult symbolic problem for mech, especially, who's the intended audience for that, we can do that now. So I'll make sure to make notes of that, especially to instructors. That like this is more for mechanics than AP1, although AP1 definitely can. Anything that's calculus based is like in its own section. All right, so here we have something near and dear to my heart as a cyclist, talking about biking with and without wind. So a cyclist is riding along a long straight road of length d, where they bike to the end of the road, then they come back. So first, we just bike at a speed v. There's no wind, we just go there and back. But in scenario 2, there's wind, where I go with the wind one way and against the wind the other. So I'm getting boosted when I'm going with the wind, speeding up my bike, and I'm going slowing down, or I'm going at a lower speed, so on the way back, due to the wind reversing direction relative to me. So we're going to end up comparing these. So this is another QQT style thing. So first, we just want to derive the expression for the time required for the cyclist round trip in scenario 1. Well, this is not hard. This is not what makes this more like a C problem, AP1, because scenario 1 is just the same constant speed. So we're just going I like to rearrange the speed formula like this. I know that distance equals speed times time if everything is constant. And in this case, the runner is just going the cyclist is going a distance 2d because they're going down the road and back. So t1 is just simply equal to 2d divided by v. As they go 2 road distances, and we divide by the same constant speed. A larger time is required for the cyclist round trip in scenario 2. Justify this claim. So sometimes, if the claim is especially difficult, I like to just tell you what it is and make you think about why. So I'm telling you that even though there's wind on both ways, and I'm getting boosted one way and getting hurt the other way, it's actually slower in scenario 2. So even though there's wind helping me and wind hurting me for equal distances, it's actually longer when there's wind. So it's actually a slower ride if there's wind and you're going on a round trip no matter what. So why is this true? Well, yes, it's true that the differences in speeds are the same, but what's not the same is the time, right? Because if I'm moving at the fast speed, I can go down that road really quickly. But if I'm at the slow speed, that takes me longer to do the same thing. So all it comes down to the fact is that yes, I'm going faster for a bit and I'm going slower for a bit, but those aren't equal times. I go slower for longer. So since you go slower for longer, uh, the speed is sort of more dragged down than it is dragged up, on average. Because average speed isn't just the average; it's a weighted average, right? If it's really, really, really windy, it's going to take you forever to get home, and that's going to make that time go up a lot. So that's what really makes this difficult to sort of thinking about it. I'm sure there's some other approaches to this too, but this is the one that I like. Um, Also, never think that my answers are the best out there. These are just how I intended it. I mean, I did write this, so this is what I was kind of thinking. Kind of that. All right, let's derive an expression for this. So we know that the total time, t2, it says, is going to be t that it takes to bike with the wind plus t that it takes against the wind, right? Because there's 2 segments. And I can't just say this for 2d equals vt because the speeds aren't the same on each segment. But I can say that the first segment has a distance d, and I'm moving at a speed v plus w. On the second segment, I'm going a distance d again, but I'm moving at a speed v minus w. And I'm kind of, this technically is like a correct response, but I'm actually saying write this as a single fraction for something we're going to do later. So what does that mean, single fraction? Well, we got to get a common denominator. So the first fraction needs the negative. The second fraction needs the positive. And then we just combine here. So again, I just got a common denominator. So we get dv minus wd plus dv plus wd. That cancels. So we get 2dv divided by, oh, what is this? Well, you can use your, what is it, FOIL. FOIL's bad word, but you know what I mean. We can do our double distributive property here, or you might just recognize this because this is a special thing. This is difference of squares. We get this. This is our time required in scenario 2, which is a lot uglier than the time in scenario 1. And what I'm claiming is that this ratio, T2 over T1, is greater than 1, which means if a fraction is bigger than 1, it means the top is bigger. So if we can prove this, we have just essentially said, yep, the wind case takes longer. So let's check that. So T2 over T1. T2 is 2 times dv divided by v squared minus w squared. And then we divide that by T1, which we said was just 2d over v. Now, you might want to write this using like keep change flip. Division of fractions can be thought of as multiplication of the reciprocal. That might help here because we got a lot of nastiness here. Goodbye 2, goodbye d. And we pick up an extra one here. So we get v squared or v squared minus w squared. So this is a lot cleaner. And this is actually sort of where we can end because notice that v squared minus anything will always be less than v squared. So what this means is that the denominator is lower. I should just use the actual words, right? I should just say this is less than v squared, meaning I'm dividing a number by a number less than that number. So this is going to be greater than 1, as expected. So that's why I consider this more of a C problem, just because there's a lot of like symbol crunching happening. I really do like this question. I don't know if this is obvious. My first thought definitely would be that the average speed is the same, because I would have just saw that I get boosted and hurt by the same amount. So I would have thought that they canceled out. But it makes a lot of sense. And if you've ever biked in wind, it makes sense as well. Just qualitatively thinking about it, like, oh, it feels like I'm biking against this wind for a while. And that really ends up dominating. Because it just takes extra time on the slow section. All right, that's constant velocity.